Hello, what I have for you right now is a problem I like to call Mumbai Miasma. And what it has to do with is outsourcing by various companies. Now, what's going on is this company that I'm talking about here used to order parts from Milwaukee where they had a 2% defect rate. And they found a supplier that was cheaper in India, in Mumbai, and they were promised this same defect rate. But the problem is, once the parts started to arrive on the factory floor, they were getting complaints from the workers about too many defects. So what they did is they decided to start looking. And what they started with was a sample of parts that came in from Mumbai, and they started with a sample of 144 parts. Of those 144 parts, what they found was a 3% defect rate. Now, actually, they didn't. I lied. They found a 3.5% defect rate. Sorry, gotta clean that up. They found a 3.5% defect rate. Now, that seems kind of high. So, they contacted you as the manager and said, we have a problem. You're going, well, maybe we do, maybe we don't. And so the first thing you start to think of is, gee, with a sample size of 144, what's the probability you'd actually get a 3.5% defect rate? So I'm looking for the probability of this sample proportion of defect rates being greater than or equal to the 3.5%. Because of course, if that could happen with a fairly high probability, then maybe you just got a bad sample and you leave the folks alone in Mumbai. So they said, okay, we want to find this. To do this, of course, you use the Central Limit Theorem. And the Central Limit Theorem suggests that in order to do this, what you need is you need to convert this to z. To do so, you find the probability that z is greater than this sample proportion minus your promised truth. And your promised truth is the 2%. And you divide by the square root of this promised truth times 1 minus the promised truth, that divided by n. Now, when you calculate this out, you will find that this becomes the probability that z is greater than about 1.28. If you look that up in your book under the normal distribution, you will find that that probability comes out to be just about an even 10%. Now, at a 10% probability, that means that it's not that unlikely that you could have gotten a sample of 144, giving you this defect rate of 3.5 if the truth really is the 2%. So there's no reason to argue with the folks from Mumbai yet. But you continue to get these complaints from the factory floor. Well, okay, so what we do is we take a second sample. The second sample is much larger. The second sample is of 500 parts. Now, I am going to say that we continued to find the 3.5% sample proportion defect rate. Okay, so now the sample size has gotten a lot bigger. What's the probability we would have gotten that defect rate if the truth was still the 2%? Well, you do the same process from the Central Limit Theorem. You look for the probability that SP is greater than or equal to the 3.5%, which of course you write in decimals, 0.035. You convert using the same technology, and the only thing that changes here is this n, and it goes from the 144 to the 500, and that makes quite a bit of difference. Because now we are looking for the probability that z is greater than 2.40. That probability comes out to be 0.0082, or less than 1%. In other words, 0.82%. Not 82%, but 0.82%, so less than 1%. Now, this does suggest that we now have a problem coming out of Mumbai. So we have to start really looking into this. To do this, the next step we're going to do is we're going to say, all right, it doesn't look like the truth is really 2%. So what I want to do is find out where the truth is. What is the defect rate they're sending us? To do that, I want to look at interval estimation or finding a confidence interval. So that's what I am about to do. And in order to do that, I want to walk you through how to do a confidence interval for a binomial type problem, because that is indeed what this is, because each part is either defective or not defective. As a result, these are all 0, 1 outcomes. All right, so what I have here is I have this 3.5% defect rate, but I'm going to do this on a sample not of 144, but the sample that I actually took, which was the large sample of 500. Now, in general, what we want to do is we want to start looking at interval estimation or confidence intervals. Now, to do that for a binomial, what you do is you take your sample proportion, or SP, add and subtract your critical value, and that critical value is from the Z table, and it has to do with just how confident you want to be of your results. And then you have your error term, which is SP times 1 minus SP divided by N. Well, okay, now let's talk just for a moment about this confidence level. Now, when we're talking about confidence levels, there are some general levels that you use all the time. Indeed, the ones that are helpful to know are percent confidence level here and the Z that goes with it. Well, okay, for 95% confidence, you use 1.96. For a 99% confidence, you would use 2.575. For 90%, you would use 1.645. And for 80%, you would use 1.28. Now, for business applications, most of the time we will use a 95% confidence level. Now, just be aware that when we're talking about a confidence levels are 1 minus what's called significance. Now, the only reason you have to know that is because at different times from different sources, people may talk about a significance level versus a confidence level. So my confidence level and my significance level, again, are related this way. So 95% confidence is 5% significance. 99% is 1%, 90% is 10%, and 80 is 20% significance. Significance is often written with an alpha. Now, again, I go back to talk about this 95% a lot because it is the most commonly used confidence level, significance level, because it's used for business most of the time. Now, if you're doing medical research, you want 99. If you're doing something like psychological research, sociological research, you might use 80. And these are just very handy to know. If you stick these in your head, and there's not a lot of numbers here, so I'm pretty sure you can do it. If you stick these in your head, it will save you a lot of time looking them up. All right, so how do I find this confidence interval? To do that, I just use my N of 500 parts. I have my confidence level, and I'm going to use business here. So I'm going to use 1.96 there. And my SP, which is my SP, which is my sample proportion, was the estimate that I found from my sample on the factory floor. So my confidence interval is going to be the 0.035 plus or minus 1.96 times the square root of 0.035 1 minus 0.035 over the n of 500. So my interval here, when you do all this lovely math, which I'm sure we can all do, this interval becomes, there it is, 0.01889 to 0.0511. That's a 0. In other words, what we have here is an interval that we are pretty sure captures the unknown truth. Now, be careful about this just a little bit, because this interval doesn't have a probability of capturing truth. What this interval is intervals created in this way, 95% of the time, will capture the unknown truth. I know those two sounded really alike, but they're not, because the interval is built on sample data, which, of course, is a random sample, whereas truth exists. Truth, I like to say, is like a butterfly. It exists. It is in one place. We just don't know where. The interval is essentially like a butterfly net, and the interval tries to capture the truth. And the size of the interval and the exact endpoints of the interval depend upon a random sample. So it's the interval that's random, not the truth. However, we still can feel pretty good. We're 95% confident that this interval captured truth. Yeah, it's not looking so good for Mumbai. I'm guessing at this point, in this not only example, but how businesses work, it's once they have this that they go, we have to contact our people in Mumbai, make them live up to the contract, or switch back because they are not meeting the promised 2% defect rate. So what I have done here is I have shown you interval estimation for a binomial and how to do a confidence interval, and we have done some binomial central limit theorems. So that is Mumbai Miasma. Thank you. I'm done.